Okay, must have been on my end. I just walked in the house. So,
Okay.
all right. Where do we want to start?
21.
21?
Yes.
All right. What is the limit of the sine of x over x as x goes to 0? This is the one they want you to just memorize.
0 over 0.
Well, that's what you get from direct substitution, but this limit is equal to 1 by definition, so to speak. You haven't had L'Hopital's rule yet, have you? Do you know how to use it?
Not yet.
But do you know how to use it?
No, I don't, unfortunately.
Take the derivative of the top, take the derivative of the bottom, resubstitute, you get your answer. The derivative of the top is cosine, which cosine of 0 is 1. The derivative of the bottom is 1. So you can find out these tougher ones, these tougher limit questions, by doing that.
Okay.
I don't know. Do you know how to take the derivative? Have you had first derivatives yet? You haven't, have you?
No, I haven't.
Well, then just memorize this. If you memorize this, it'll satisfy a lot of these questions. Okay?
Okay.
Notice that 21 is the same as this. Only instead of x, it's root 2 theta. But as long as that is the same as that, then the limit is 1. It doesn't matter how complicated it is. I could say, what is the sine of x minus 1 over x minus 1 as x goes, well, I better not say that. I'm going to confuse you and maybe myself. Just memorize this. Okay?
Okay.
So 21 is 1. 22 is not quite that. K is some constant, okay? So it's not over KT, it's over T. Well, how can I make it over KT? Because if I had a K in the bottom, then I know this limit is 1.
So multiply by K.
Multiply top and bottom by K. Well, here's the top multiplied by K. Here's the bottom multiplied by K. Now, I know what that limit is. What's that limit?
It would be 1.
Times K. So this limit is K.
Okay.
'23. Similar, but slightly more complex, because now you have the limit of the sine of 3y over 4y. Well, our goal is to make this 3y. Right? In other words, if it was the sine of 3y over 3y, I know that limit is 1. You with me? If you don't understand something, be sure and stop me, and I'll try to explain it a different way.
Yes, please. Please explain it a different way.
You want me to explain it a different way?
Yes, please.
Okay. So if I had the limit of the sine of 3y over 3y, then let's use substitution if you need to. Let's let u equal 3y, and then we end up with the sine of u over u. Well, that looks a lot like sine of x over x.
Okay.
So we know that limit would be 1.
Yeah, that's correct.
This limit right there has to be 1. And it doesn't matter whether it's x over x or 3y over 3y or 17y over 17y. As long as that's the same as that, then this limit is going to be 1.
So I'm trying to make the 4y 3y.
Yeah, how do we do that?
Subtract 1y.
Can't do that. We don't want subtraction going on. I got to multiply top and bottom by some number to turn this into 3y. What would it be?
So I would have to multiply
Uh-huh.
Everything by 0.
In other words, if I were to do what you suggest, which is that, well, I got to do it to the top also. Now the top is all messed up. I got 3y on the bottom, but the top doesn't have any longer what I started with. So I wouldn't know what that was. So I got to multiply the bottom by 3/4. That'll turn that into 3y. And because I'm dealing with a fraction, whatever I do to the bottom, I got to do to the top. Well, I'm multiplying the 3/4 in front of the sine function because I don't want to change that 3y. That 3y is good. Okay? And now this turns into 3/4 times the sine of 3y over 3y. I know that limit.
Okay.
So it's 1 times 3/4, or the limit of this problem is 3/4. Okay?
Yes. So next is 24.
All right, 24. The limit as h approaches 0 from the left of h over the sine of 3h.
So would I just plug in 0?
Question is this limit, is this limit also equal to 1 as x goes to 0? Is that equal to 1? I would bet my right arm on it that it is.
Because it would be 0 over sine of 0.
If the limit of sine x over x is 1, then the limit of x over sine x has to be 1 also, I believe.
Okay.
Incidentally, if I graph sine x over x on Wolfram alpha, it looks like this. Goes up to 1, comes back down, and starts approaching the asymptotes again. So that's what that graph looks like, sine x over x, with this value being 1. And this graphically shows you why that limit is equal to 1. You can tell that as we approach 0, from either side, we're approaching 1. Now the question is x over sine x? We're just going to, you know what, I better graph it. Hold on. Let me pull up Wolfram alpha. I can't imagine that it's not 1. Computer's running a little slow. I want to graph x divided by, well, first of all, let me show you sine x divided by x.
Okay.
So that you can see why the limit of this is 1 as x approaches 0. See why?
Yes.
Okay. Now I'll do the reverse. X over sine x. X divided by sine x. We'll see what that limit is as x goes to 0. Guarantee it's going to be 1.
But it's different.
No, it is. It's 1.
Okay, never mind. Yeah, you're right. This looks different.
Yeah, it does look a little different, but it's still 1 because the reciprocal of 1 is 1.
True.
But let's see if they tell us that. No, they don't tell it to us. But you're right, it definitely looks different. But I think we can assume that it's 1. So what do I need to do to the top?
So it would be 0 over sine of 3h.
I'm going to multiply the top by 3 and multiply the bottom by 3. And now I know the limit of that is 1 times 1/3. So this whole limit is 1/3, not 3. This 3 on the bottom is in the bottom.
Okay.
Okay. So in other words, the limit of this is 1, which makes 1 over 3.
Okay.
All right, 25. Do we have answers on the odd ones?
Oh, yes, I do. I can pull them up right now.
All right, well, until we need it, let's not worry about it. All right, let's see. Limit of the tangent of 2x over x.
So I'd have to multiply everything by 1/2. Or
By 2.
multiply the bottom by 2.
Well, the problem is I'm not sure what the limit of tan of x over x is. Are you allowed to use a calculator on doing these?
Yes, I am.
For your test also?
Yes.
Well, let's have a look at Wolfram Alpha and see what tan x over x does. Looks like it goes to 1, right?
Yes.
Definitely goes to 1. Not just looks like it, but definitely goes to 1. Okay, so what do I have to do to this?
I have to make 2x on the top and a 2x on the bottom.
Okay, so what's this whole limit going to be?
Tangent, or 2 tan 2x over 2x.
And what's the tan of, so you're right, it turns into this. What's this part equal to?
It'll be 2 over 1 altogether, I think.
2 over 1. 2 times 1.
So after it's 2 times 1, it'll be 2.
Yeah, so the limit is 2.
Okay.
Okay. Yeah, if ever you have troubles figuring out what these limits are, plot this function, because we know we can make this look like tan x over 2x, or tan of 2x over 2x, is what I meant, by multiplying top and bottom by 2. And then as long as we know what tan of 2x over x is, notice that if I put a 2 in front of here, it's not going to change the limit. If I put a 2 in front of the bottom and the top, watch what my limit is. It's still 1.
Yeah, you're right.
No, it isn't. What the heck happened? Oh, it didn't go in there. Ah, it didn't go in there right. Why didn't it? Tan of 2x divided by 2x should not have come out. They got the wrong input here. Let me put parentheses around everything. See if that helps. Tan of 2x divided by the quantity 2x. Let's see if at least we'll show my input correctly. Yeah, there it is. And there's the limit of 1. In other words, that curve looks real similar to the tan of x over x, doesn't it? For the moment, I need you to understand that if the limit of the tan of x over x is 1, then the limit of the tan of 2x over 2x is also 1. Or the limit of the tan of 17x over 17x is 1. In other words, it doesn't matter that that's 2x instead of x. As long as that's the same, then this limit is 1.
Okay.
It's always going to be the same as the limit of tan of x over x. And you can think of it as substitution, okay? Let's use substitution. Let's let u equal 2x. Well, now this becomes the tan of u over u. Well, that's the same as the tan of x over x. So this limit has to be 1. So the tan of 2x over 2x has to be 1. Important concept on all of these problems, because that concept is going to apply to virtually every problem we see here.
Okay.
So it's very important to understand it. Now, 26, they do this reversing again. And again, let me graph t over tan t, but I'm sure that that's going to end up being 1 also. T over, or rather x, divided by tan x. Let's look at that curve. Limit equals 1, right there.
Okay.
Okay? You can see the y grid is different than the x grid here. That's -1, that means that's +1. So it is the same. So basically what you need to memorize is that even if you reciprocate it, it's the same limit. As long, in other words, before we were trying to figure out what the limit of x over sine x is. Well, if the limit of sine x over x is 1, then the limit of x over sine x is 1. Just like if the limit of tan t over t is 1, then the limit of t over tan t is also 1. Because the reciprocal of 1 is 1. So how do we make the top look like we need it to look? In other words, I want t over tan t. How do I make that function look like that?
I can't divide, can I?
Well, you can multiply by 1/2. Let's multiply the top by 1/2 and the bottom by 1/2.
Okay.
Okay, now what's that become? That becomes t in the top, and it becomes 1/2 of tan t in the bottom. We know that's equal to 1. 1 divided by 1/2 equals 2. So this limit equals 2 on 26.
Yes, since we do reciprocal multiply.
You know
Okay.
what? I didn't need to do any of that. I just realized by looking at it is all I needed to do was separate that 2 from the t. In other words, it was already done for us. I didn't need to do anything to this. There's my 1 right there, times 2.
Oh.
Yeah, this was real easy. I didn't actually need to do that, multiply top and bottom by 1/2. Gave me the same answer as it should, but it wasn't really necessary. Whereas notice here, I can't really do that. I can't take that 2 anywhere. I can't separate it from the tan function on 25. So the only way I can do 25 is by multiplying top and bottom by 2. But 26, I don't need to do that. If I'm trying to produce a t over tan t, is all I got to do is separate that 2 out and put a dot in between them.
Okay.
All right, now we're getting into different kinds of functions. Well, let's see. We got an x. Cosecant is 1 over sine. So let's see. X cosecant 2x. Do they have you use the calculator to come up with some of these or not?
I can use a calculator because we're taking the huge examine, so they'll let us use a calculator on anything.
On all of it?
Yes.
Let's see if we can figure this out here. Well, let me think for a moment. Let's see. Do we know the limit of x over cosine x? I don't believe that is 1, because no, that would be 0 over 1. So that would be 0. So cosecant is reciprocal of sine, so that's undefined at x equals 0. So if I were to do direct substitution, this is what I would get. I would get 0 times undefined means infinity. That's what the cosecant of 0 is infinity. And I'm dividing by the cosine of 0, which is 1.
So it would be 0 times infinity over 1.
0 times infinity is indeterminate. We don't know what that is. It's the only time when you multiply something by 0 that you don't know the answer is 0, is when the thing you're multiplying it by is infinity. There's a bunch of indeterminates. 0 over 0 is indeterminate. Infinity over infinity is indeterminate. By indeterminate, it could be anything. We don't know until we do further work. Infinity minus infinity is indeterminate. All of these, you don't know what they are until you work on it further. So we got to do more work on this to figure it out. So direct substitution doesn't help. I could use L'Hopital's rule, or I could graph it. There is a nice advantage to graphing it, and that's you get your answer without knowing how to do it. And in other words, all you have to do is look at the graph. What kind of calculator will you be using? An Inspire or a TI-84?
TI-84.
Well, you know how to put in this function, don't you?
Yes, I believe so. Do I don't know how to do cosecants and things like that. I only know weird.
Problem is our answer might be 2/5, I suspect, and that might be hard to read off the graph. Although you could always find that point, I think. Just a second here. Let's have a look graphically at some of this function. Let's first of all figure out whether there's, well, I know what the limit of x over cosine x is. That's 0. Now we have 0 times infinity. So let's type the whole function in. Cosecant 2x, I'm going to need parentheses around all of this, I'm sure, divided by the cosine of 5, I bet I need parentheses around that also, 5x get it in there right? Yeah, I did. Now, that's the number. We're trying to figure out what it is. In other words, if you could zoom in on that and figure out where that local minimum was on your calculator, you'd get that value. You know how to do that?
Do I have to? Oh yeah, actually I do.
Yeah, in other words, if you zoom in on that and request
right.
local minimum and then put your trace to the left and to the right, it'll give you the y value of that point as we approach 0. And that'll be the answer. And like I said, I think it's probably going to be 2/5, the ratio of these two numbers. I hate to do it by this technique, though. Because there should be an algebraic way to do it. There's another one that they want you to memorize. You've probably seen this one. Maybe we can apply this one to this problem. And that's the limit of 1 minus cosine of theta all over theta as theta goes to 0. What's that limit? You know? In other words, if you substitute, you'll get 0 over 0. That limit actually is 0.
Yeah, that's true.
That's one that they want you to memorize also. Let me graph that real quick. We got the quantity 1 minus cosine of x divided by x. And we'll watch what it does when x goes to 0 and the function goes to 0. Right there. Okay. But again, that's one they just want you to memorize.
Yeah, I remember that on the unit circle too.
Maybe if we rewrite we could figure it out. Let's see. If I rewrite this as x over, the cosecant is sine in the bottom, right? So if I rewrite it, now we're getting somewhere. Yeah. Now what can I do? In other words, now I've got a key part right there. If I can get the top to say 2x, I know what that part of the limit is. Right?
Yeah, so it would just be...
What would I have to do? Multiply top and bottom by what number?
1.
2. It's got to be 2x over sine 2x. First of all, I don't know what x over cosine x limit is. I've never been taught that one. So, but what I do know is that limit if this argument is the same as this numerator. Okay, well I can make it the same by multiplying top and bottom by 2. There's the top multiplied by 2, there's the bottom multiplied by 2. And now what I have is 2x over 2 sine 2x times 1 over cosine of 5x. See where that's exactly the same as what we started from? In other words, what I got on the far right is this over here. And I know what that limit is. What's that limit?
1. 1/2. 1/2. Okay.
Remember, that limit is 1. 2x over sine 2x is 1, but I still got this 2 in the denominator over here. So that limit's 1/2 times, well, when x goes to 0 here, this denominator goes to 1. So that's the limit, 1/2. It's not 2/5, it's 1/2. And is all I had to do to solve it was to get it into the form of something that I knew the limit of. I know the limit of 2x over sine 2x is 1. So I had to make that top numerator have the same argument as the sine has. So that's why I had to multiply top and bottom by 2.
Okay.
All right, let's go to the next one. 28. Wow, boy, these don't get any easier.
No.
Although you can kind of see what I'm doing on all of these, I think. Some of these limits you can figure out by substitution once you get part of it taken care of. As x goes to 0, I'm going to have 0 over, well, the tan of 0 is 0, so the cotan must be infinity, right? The reciprocal, when you divide by 0, this is infinity. So already I got 0 times infinity. Well, I have no idea what 0 times infinity is, so I have to rewrite it. Okay, so let's make cotan 1 over tan. And then let's make cosecant 1 over sine. So what I really have is 6x squared over tan of x sine of 2x. And I can take the 6x squared and write it as 6x times x. And I happen to have a fair idea of how to figure that limit. And I have a fair idea how to figure that limit.
Right.
You see how we're going to do it? Taylor, you still there?
We're lagging.
What's that?
Can you hear me?
I can hear you.
Okay, we're lagging a little bit.
Can you hear me is the question.
Yes, I can hear you now.
Okay. I can hear you just fine. So
okay.
We need to separate this thing out. Let's separate that and make it the product of those two functions. Because I know I can figure out the limit of that, and I know I can figure out the limit of that. You with me?
Yes.
Okay. So this becomes 6x over tan x times x over sine 2x. Now, what do I have to do to the left side? I know what x over tan x, that's 1.
So would I cross out the x and the tan x to make it 1?
Yeah. In other words, I can even take that 6 further and put it over here. Like this. Okay? Now, I know that limit is 1. What do I have to do to this to figure out how to solve that?
Say that one more time.
What do I have to multiply top and bottom by so that I can figure out this limit on the right?
2.
Okay, so I multiply the top by 2, I multiply the bottom by 2. Now I got my answer. The limit when I substitute 0 for x is going to be 6 times, well, I know this is 1, and I know this part is 1, so the whole thing is 1/2. And that number is 3. That's our limit.
Okay.
Okay. So this is not that different from polynomial limit questions in that you notice what I've been doing here is factoring. I factored the top. Instead of making it 6x squared, I made it 6 times x times x, which is factoring. Okay. Now let's look at 29. 29 is going to invoke this other thing, so let me list it. We know that the limit of 1 minus cosine theta over theta as theta goes to 0 is 0. We know that. Okay, so let's look at 29. We got x plus x cosine x. Notice that if I factor out an x, I'll have 1 plus cosine x. And in the bottom, I got sine x over cosine, or sine x cosine x. Well, let's see. The numerator certainly goes to 0, and the denominator goes to 0. So, as all tough limit problems do, upon first substitution, you get 0 over 0.
Okay.
Okay. Let's see. If I employ factoring here, I got x times 1 plus cosine x in the numerator. And in the denominator, I got sine x times cosine x. Well, I can do some splitting up of that. In other words, this whole thing is x over sine x times 1 plus cosine x over cosine x. And now we have our answer. As x goes to 0, what's that go to?
That would be 1.
And as x goes to 0, what does that go to? Just do a direct substitution.
Okay, it would be 1 plus cosine of 0.
Which is?
0.
No. You got to know your trig functions really good. Cosine of 0 is 1.
But yeah, it would be 1 because it moves to the right. Okay.
Yeah, okay, so I end up with 2 over 1. And the answer is 2. So again, factoring. Factoring and separating. Factoring and separating, and use what you know about certain limits, like sine x over x over sine x, tan x over x over tan x. You know what those limits are as x goes to 0. So your goal is to take all of these functions that are more complex and separate them into stuff that you know and stuff that you can figure out using direct substitution. Kind of the same as when you're doing limits with polynomials. Not that different, really. All right, 30. what are we going to do at the top? Oy, it's ugly. No, not that ugly.
So it's x squared minus x plus sine x.
And we work with that.
So I'd have to multiply by...
First of all, tell me, can we work with that? In other words, if I gave this problem only to you, would you be able to figure out its limit as x goes to 0?
I think so.
Yeah, by multiplying top and bottom by 2.
Yeah.
Oh, no, by just separating the 2 out. Yeah, this is another one of those where you don't need to multiply top and bottom. In other words, as long as I make the bottom look like this, 2 times x,
it's a reciprocal.
I already have it. I know that's 1.
Oh, yeah, you can separate it. Okay.
Okay, so now let me separate it completely. I got x squared minus x over 2 times sine x over x. Well, I know what that is. That's 1. Question is, what is this as x goes to 0?
It would be 0 over 2, but that doesn't work out.
That's 0. No, it does work out. 0 over 2 is not indeterminate. 0 over 2 is 0. So we got 0 times 1. This limit is 0.
Yeah. So as long as there's an actual number and not 0 over 0, it's okay?
Yeah. In other words, if I have 0 over 3, that's 0. If I have 3 over 0, that's infinity or undefined. But it's infinity in terms of limits. In other words, if I said to you, what is the limit of 3 over x as x goes to 0 from the right? That's infinity.
Okay.
As x keeps getting smaller and smaller and smaller, the answer keeps getting larger and larger and larger. Now the reason I said 0 from the right is because if I go 0 from the left, it goes to negative infinity. So actually the limit at 0 does not exist, but the limit as x goes to 0 from the right is positive infinity. So the only time I ever have problems is when I got 0 over 0. Okay, let's look at 31. We got 1 minus cosine of theta over sine of 2 theta.
So I would have to... Could I move the 1 to the back of the cosine to the other side?
Can you do what?
Could I make it so it's cosine minus 1?
Well, here's the one that we know. 1 minus cosine of theta over theta is equal to 0. But we don't have that. We have 1 minus cosine of theta over the sine of 2 theta.
So multiply by 1/2?
No, that's not going to help either. I'm thinking. If we use a trig identity here, remember those two limits. You got to memorize both of those and know them, and you'll use them frequently on every question here. And that's sine x over x, know that limit. Know the limit of 1 minus cosine theta over theta. That limit is 0. And know the limit of tan x over x. That limit is 1 also. Now, how am I going to, let's see, if I were to use the double angle identity, this becomes 2 sine theta cosine theta. That doesn't help very much. That doesn't help at all. This is 31, and we actually can figure out an answer or look up an answer on this. I wonder if we want to multiply by, let's try that. Let's try multiplying by the conjugate. Remember the limit problems? There were 3 ways to find them when you're dealing with polynomials, and one way was factoring, but another way was multiplying by the conjugate, which frequently helped. Okay, well, if I multiply by the conjugate of the top and bottom, just multiplying it by the number 1, so that's allowed. Now in the top, I got 1 minus cosine squared of theta. Guess what? That's equal to sine squared of theta. So let's see. You with me?
Yes, I'm listening.
Okay. No, by that I mean when I say you're with me, you understand what I'm saying?
With the trig functions or the identities?
Well, I decided I would try multiplying by the conjugate of the numerator because that'll create 1 minus cosine squared, and that can be replaced by sine squared.
Okay.
Of theta. So this is where I'm at now, and now I'm going to erase this numerator and replace it with sine squared of theta, which is sine of theta times sine of theta. Now let's see, as we go to 0, we still got 0 in the numerator and 0 in the denominator.
All right. So it'll be 0 minus sine of 0.
Well, hold on. Let's go back and substitute for sine of 2 theta that identity, which is 2 sine theta cosine theta. Now that might be useful, because now I can cross one of those out with that, right?
Yes.
Okay, and what does that leave us? Now we're going to have sine theta over 2 cosine theta, 1 plus cosine theta, and remember the denominator doesn't go to 0 now. The numerator goes to 0, but the denominator goes to a number. That goes to 1, that goes to 2. So the denominator goes to 4, so I end up with 0 over 4. What's the limit of this? If it's 0 over 4?
It would be 0.
You look up 31?
Yes, I'll do that right now. Get into the chapter real quick. It says that it would be 0.
Yeah. In other words, you don't always have to, the only thing you have to do to these is manipulate them so that you don't end up with 0 over 0. And I don't here. I end up with 0 over 4. Well, 0 over 4 is an easy limit to understand or figure out. That's 0. But this was a pretty tricky. I may have done it the hard way because I did a lot to this. I multiplied by the conjugate, and then I used the trig identity, and then I started canceling stuff, and by doing all of that, I ended up with something that's no longer 0 over 0. And that's all you have to do, is get it to where it's no longer 0 over 0. Let's do 32. It looks equally hard. And when you see that, think factoring immediately. Okay, so I'm going to factor out an x, leaving 1 minus cosine x. The bottom, I'm going to split it up so that it's sine of 3x times sine of 3x. Both of those steps are logical. Why? Because I see something there I know how to do.
So then I'll multiply both by 3.
I'm sorry, I couldn't hear you.
I'll multiply both by 3 at the top and bottom.
Right, so I can do 3 there and 3 there. And now the part that I have circled goes to 1/3. Okay?
Yep.
And it's being multiplied by 1 minus cosine x, which does not go to 0. That goes to 2 over sine of 3x that goes to 0. So now I've got 1/3 times 2, excuse me, it is 0 over 0. What was I thinking? No solution yet. I was thinking that it wasn't 0 over 0 anymore, but it is. Cotangent goes to infinity. So we end up with a bunch of indeterminates at this point, even if I substitute x for 0. I still end up with 0 over 0. I know what 1 minus cosine x over x is, but we don't have that. Oh, what happened to my x? Oh yeah, no, I took care of my x in this part here. Let me go back a step. I know we don't have much time here, but let me just see if these get progressively harder. I hope they don't give you these hard ones on the test. Let me go back to this point here. I certainly can separate it into two fractions. In other words, I can separate it into that times that. And the circle on the left I know goes to 1, but what I got on the right is still 0 over 0. Let's try that trick I just did. Multiplying by the conjugate. In other words, whenever you see expressions like 1 minus cosine, it means if I multiply by the conjugate, I'm going to turn that into 1 minus cosine squared, and that's going to convert to sine squared.
Okay.
I'm not sure that helps us, but let's see. So now the top becomes 3x times 1 minus cosine squared x, which is, let me erase that and write sine squared. You really have to know your trig for, and I'm going to write sine squared as sine times sine. So that's what my new top is going to be. My new bottom is 3 sine 3x times sine 3x. And I know what that is, but the rest of it is still 0 over 0. I haven't accomplished. Oh, no. I still got a 1 plus cosine 2x as a multiplier. And that goes to a number. So this whole thing goes to 0. No, it doesn't. Excuse me. It does not. I still end up with 0 over 0. I don't have any way of handling that yet. Well, as a last resort, you can always graph these and see if you can figure out the answer from the graph. In fact, you definitely can, right?
Okay.
I mean,
yeah.
You see how that's always a solution with every problem on here? In other words, put that full function into your graphing calculator and then look at it and see, well, what happens to the function as x goes to 0? Does it approach a clear number? Does it approach 0? Or does it approach 1? Or in one of the cases, that one, it actually approached 1/2. And that was the answer, 1/2.
Yeah, it was the answer.
You can solve all of these graphically. They're far more difficult to solve algebraically. As you can see, the difficulty I'm going through on every one of them. Every one of them is a high degree of difficult limit question. In fact, I do a lot of tutoring on limits, and I don't get these kind of difficult questions, not like you're getting here on this page. These are about as hard as I've ever seen.
Wow.
You go to a private school, so don't you?
Yeah, we're using the book from MIT, my teacher said.
Okay, well, there's your explanation right there. Private schools frequently are not just Common Core. In other words, most of my students stick to Common Core, but every now and then the private school students or somebody going to a honors course or something, they'll end up with these higher degree of difficult questions that are really tough to figure out. And look, they get harder as we go down. The sine of h, are you kidding me?
Yeah, it's pretty difficult.
Well, it's probably difficult. Might not be that difficult. I don't know. I'd have to look at each one of these one at a time and give it a lot of thought to see if I could figure out how to solve it algebraically. But the moment you reach that point where you don't know how to solve it algebraically, then just graph it and see if you can figure out the answer from the graph.
Okay.
Okay? Wish I had more time to spend with you on this, because I see that, well, some of these are really going to be tricky. But eventually we would figure out the algebra on all of them and be able to do them all algebraically. It just might take 10 minutes per problem to do, and the harder they get, the longer it's going to take. But the quick and dirty way to do it is definitely graphing. All right? All right, Taylor. We'll talk to you later.
Thank you. Have a good evening. Bye.